So in this video, I'm going to be listing a few different ways that we can create the equation of a line in a two-dimensional plane. The first way is the slope-y-intercept form, which I'm sure that you're all very familiar with. So this is your y equals mx plus b. I'm sure by now you know that in order to use this equation, you're needing the slope and a point in order for you to plug that information in and solve for your b value or your y-intercept. The second set or type of equation that we're going to be looking at is called a vector equation. So what that is some vector r is equal to r sub 0 plus some parameter t times the direction vector m. And here we're going to be saying that t is an element of the reals. So what this looks like in Cartesian vector form or component form is this. So this r sub 0 is really just a point that we're going to make look like this using our square brackets so that everything looks the exact same, times parameter t times that position vector m, and still t is an element of the reals. The next equation is the parametric equation. So this is taken directly from the vector equation, and we're going to be breaking it up into components. So if I'm looking for my x component, we need to be looking at just the x components or parts of the vector equation above. So x is equal to x sub 0 plus t times m1. And if I'm going to do the exact same for y, I'm going to be getting y sub 0 plus t m2. Now we do need to say for both of these that t is an element of the reals. The fourth and final equation that we're going to be talking about today is just the exact same as the standard form that you previously know, but we are going to be giving it a new name so that when we're dealing with 2 dimensions and 3 dimensions it is easier. So this will be called the scalar equation. So a couple of things that I want you to notice about this. So the first thing would be everything is on one side and it is equal to 0. The second thing that I do want you to just kind of take note of, I guess, is that from this equation I can create a normal vector. So my normal vector, remember, will be perpendicular to the line. And we can create this normal vector that is just the components A and B. So this will be helpful in some questions in this chapter, knowing that we can create the normal using the scalar equation. Even though the equations that I previously talked about on the past page were used for 2 dimensions, we can use them for 3 space as well. So if you can see, I rewrote the vector equation from the previous page, and right below I have written what it would look like if we were talking about something in 3 space. So our coordinate x, y, z can be rewritten as x sub 0, y sub 0, z sub 0 plus some scalar t times the direction vector m1, m2, m3. Still, t is an element of the reals. The next thing that we're going to be looking at is our parametric equations. So this is the equation that we kind of looked at the vector equation for to create. So this time, the only difference is when we're doing this, I'm going to be getting 3 equations. So x is equal to x sub 0 plus t times m1. Y is equal to y sub 0 plus t times m2, and z is equal to z sub 0 plus t times m3. And again, t is an element of the reals. So just like before, in order to use these equations, we do need 2 pieces of information. So if we know the direction and we know a point, we can use either of these to create the equations. The first example that we're going to be doing here says create vector and parametric equations given the set of points a 2, -1, 5 and b 3, 6, -4. So the method that we're going to be using is very similar to the method that we would be using if we were still working in 2-space. If we were working in 2-space, what we would be doing is finding the slope and then using that slope and finding our b or our y-intercept. Since we're in 3-space, we are going to be doing, like I said, something very similar. So the first thing that we're going to be doing is finding our direction vector m. So our direction vector m is the exact same as our vector ab. So as you remember from before, if we're trying to figure out our vector ab, what we need to be doing is taking the coordinates in b and subtracting the ones from a. So what we have here first is 3 subtract 2, so 1. 6 subtract -1, so 7. And -4 subtract 5, so -9. Now remember, what that gave us is the direction vector, or our vector AB. In 2-space, after we had our slope, we would then use any of the points, so either point A or point B, and we would use that to help us find our B or our y-intercept. When we're writing our vector equation in 3-space, it is going to be very similar, so we are able to use either point A or point B and the direction vector that we just found to help us write our vector equation. So when I'm writing my vector equation out, I have x, y, z is equal to, I'm just going to choose point A just because it's the first one that I see. So 2, -1, 5 plus t times the direction vector AB that I just found there. And again, we do need to say that t is an element of the reals. Once we have our vector equation, we know that we're basically done. The parametric equations are very easy to find once we have that vector equation. So if I'm going to be writing my parametric equations out, I'm just going to be using each component and reading it separately as I go. So x is equal to 2 plus 1t. Y is equal to -1 plus 7t. And z is equal to 5 minus 9t. Now again, t is an element of the reals. So what I could do to extend this question even further, so this question the way it is done, but I could ask you, is point C, whatever point I decided to give you, also on this line? If I asked you this, what I would be able to do is just take the point that I gave you and plug it either into the vector equation or the parametric equation and make sure that that point satisfied the equations that we have. So I think what I'm going to be doing is I'm going to be adding a part B to this example. I'll do that on the next page. So here we are with part B. Is the point C 0, -15, 9 on the line above? So just in case you're not writing these notes down, I did rewrite the parametric equations that we found on the previous slide. So what I need to be doing is I need to be taking this point C, my x, my y, and my z, and I need to be plugging it into the parametric equations that I have here and making sure that they are satisfied. So let's just get started plugging these numbers in. So I am going to have 3 equations here. So 0 is equal to 2 plus t. My second will be -15 is equal to -1 plus 7t. And my third, I'm just going to squeeze it in here, 9, oh my goodness. Let me just erase this for 1 second here. 9 is equal to 5 minus 9t. So I'm just going to go ahead and solve, and what I'm going to notice is that if every single t value that I solve for is the same, then that point would be on that line. If any one of them is different, then the point is not. So what I'm going to get when I'm looking at this first equation is t is equal to -2. In my second equation, I have negative 15 plus 1, so a negative 14 divided by 7. So again, t is equal to negative 2. And in this third and final equation, I get 9 take away 5, so a 4 divided by negative 9. So right away I know that this is not the same, not negative 2, so I know that the point C is not on this line. In terms of a final statement, I don't need anything other than, therefore, this point is not on the line.